So in a previous video, I was going over how to draw Lewis structures. Remember, Lewis structures show the types of bonds and the location of non-bonding electrons. Another thing that Lewis structures can help us determine is the molecular shape, or we can call it its geometry. So we're going to use something called the VSEPR theory. And here it is in the notes right there in the middle. I'm saying VSEPR, which stands for valence shell electron pair repulsion. So if you look, there's the VSEPR. That's what VSEPR stands for. It's just an acronym for valence shell electron pair repulsion. So that's a lot of words, but we know that it's the valence electrons that are involved in bonding. So it says valence shell electron pair. That's just saying the valence electrons. And then repulsion, we know that all electrons are negative charge. So if an atom was surrounded by electrons with a negative charge, that those electrons would repel or push away from each other. So the VSEPR model for determining shape uses the idea that electrons around a central atom will create a shape where the electrons can all be as far away from each other as possible. So that's kind of how it works in terms of logistics. Like that's what they're trying to do. Now, in order to figure out a shape, and I have a handout on the next slide to help us do this, but to determine the shape, look right here. The second thing down. So to determine the shape around an atom, we have to determine the groups that are surrounding the central atom. Now, in a second, I'm going to tell you about groups, but I want to tell you a limitation with the VSEPR model is that it treats each atom as a central atom. So in the models we do, we only have one central atom, so that's not really a big deal. But for larger molecules, every connected atom would have to be treated like a central atom to figure out the shape. So it would almost be like putting a puzzle together, because you'd have to figure out the shape of the first thing and then attach the shape of the second thing, and it just kind of keeps building. So it is a limitation that you're only looking at one central atom. All right. So going back, it says determine the shape around a given atom, the central atom. First, determine how many groups. Now, what groups can be, they can be an atom that's bonded to the central atom, or they can be lone pair or those non-bonding electrons. So that's what we're talking about in terms of groups. An atom that's bonded to the central atom, or lone pairs that are on the central atom. So I'm just writing there, we're going to refer to the central atom. All right, so let's take a look at the handout, and then I'll do some examples with you. So here's the handout. So you'll notice here we have an electronic geometry. In the electronic geometry, it does not distinguish between the number of atoms and the number of lone pairs. It just counts all the groups. Okay, so we'll look at both of them here. Then over here on this one is the molecular geometry, and this is also known as the shape. So if something's asking you for the shape, they're referring to this molecular geometry. Now, the shape is determined both by the number of atoms in comparison to the number of lone pairs. So to get to the shape, you have to divide up into atoms and lone pairs. And I'm going to write on this on the central atom. So when we're talking about atoms and lone pairs, we're referring only to the ones located on the central atom. Now over on this far column, to me it's not super helpful, but those are just examples. All right, so I'm going to use some of the examples that we had in our Lewis structure lesson. So if you want to know how I'm getting these Lewis structures, then go back and watch the video on Lewis structures, or you can try to do them yourself. All right, so the first one is H2S, which had the Lewis structure that looked like this. Now, Lewis structures don't have to show shape. They're just showing the atoms. All right, so our central atom is sulfur. So this is the one we're going to pay attention to. And there's two things we have to account for. One is how many atoms are bonded to sulfur. And so I see 2 atoms bonded to sulfur. 1, 2. And then looking at the sulfur, I also have 2 lone pairs. 1, 2. Okay, so looking at that, there's 4 things total. So with our electronic geometry, that would be down here. These are 4 total, right? Because it has 1, 2, 3, 4. So our electronic geometry, I'm just going to put EG, would be tetrahedral. That's what that is right there. The molecular geometry, or the shape, that's where you break it into the 2 pieces. So it's 2 atoms, and here's 2 atoms, and 2 lone pairs, and 2 lone pairs. So notice it's in one of the tetrahedral choices, and if we come here, it's tetrahedral bent. And sometimes they just write bent. The person who made this handout put tetrahedral bent because up here, see on the sheet, there's also another bent called trigonal planar bent. So to distinguish between the two, they wrote tetrahedral bent. So the shape of the H2S is tetrahedral bent. So if we were to draw the shape, here they've tried to draw it, so that's an example of water, but you had S, and then we would have lone pairs, and then what they've tried to do, if you look down at the sheet, if it has a dashed line, it's supposed to be behind, and if it has a thick line, it's supposed to be coming out, because it's supposed to be 3-dimensional. Oftentimes the bent ones, I draw it like I was looking face on and make it more like that. So it has a bent shape. All right, let's try another one. I'm going to erase all of this that I wrote here because we might not do that one again. Okay, so the next one I want to try, I think I had CCl4. And then it had lone pairs on all the chlorines. So what I'm drawing here is the Lewis structure that we came up with in the Lewis structure video. Okay, so there's the Lewis structure. And then now let's say the question was, find the shape. Okay, so you have to look at the central atom. That's what shape has to do with. And you don't have to draw all the lines. I'm just doing this for emphasis. Okay, so then we look at it and we say how many atoms are bonded to the central atom. And I count, there's 1, 2, 3, 4. I do not care that they have single, double, triple bonds. That's irrelevant. The question is how many atoms are bonded to the central, not including the central, but how many are bonded to the central. So there's 4 atoms, and then looking at carbon, because we only care about the center, there are 0 lone pairs. Now I know there's lone pairs on the chlorine, but that doesn't impact the shape. It's only what is around the central atom. So again, this would have 4 total. So if I was asked to find the electronic geometry, I'd need the one, anything with 4 is down here. This is tetrahedral. That's the electronic geometry. If you look above it, trigonal planar, that has 1, 2, 3 things around it. So then tetrahedral, though, this is 4, 0. So last time we were at 2, 2. Well, that's not what we have. We have this one right here. 4 atoms, 0 lone pairs. So 4, 0 is also called, the molecular geometry or the shape is also called tetrahedral. What you notice with these is if there's no lone pairs on the central atom, the electronic geometry and the molecular geometry or the shape are the same if there's no lone pairs on the central atom. Now, to draw the tetrahedral, it looks kind of like a tripod. So you would have like a carbon in the middle. I'm going to get my black marker. So we would have a carbon in the middle. It looks like one of them, the chlorine, would be sticking up. The other one would be in the plane sticking down. And then there's one going behind the board trying to draw 3-dimensional and one coming out of the board. Oops, why am I drawing hydrogens? Just a second. Let me go back. Okay, back. It was chlorine on this one. Chlorine, and then one coming out. This, what I'm drawing here, the shape is kind of a variation of what they call a VSEPR drawing. So a VSEPR drawing is just when you try to draw the shape. VSEPRs don't have to include the lone pairs around the outside atoms, the periphery atoms. I'm just doing it because it helps me see the whole picture. All right, so there's 2 examples. So see what we're doing. We're counting how many atoms on, let me back up. We're starting from a Lewis structure. We're counting how many atoms are around the central atom and how many lone pairs are on the central atom. So let me erase this slide. I'm going to erase it and do 2 more practice problems. If you want to see these practice problems again, you can rewind the video. They won't be erased on the video. We're just kind of cleaning the slate to move forward. So I want to do an example when I have a multiple bond. So another thing we did was CH2O when we did Lewis structures. And carbon was in the middle, and then we had an oxygen with a double bond, and then 2 hydrogens. So again, what we'll find is our central atom. That's what we're looking at. And we first say how many atoms are bonded to it. And I see 1, 2, 3. And how many lone pairs are on the central atom? So carbon has no lone pairs on it. And that's what will determine the shape. So there's 0 lone pairs. Lone pairs, for example, if there was lone pairs, you would see dots on it. That's what a lone pair is. but there's no dots. I just drew those. So this has 3 total. Okay, so we're in this section here, 1, 2, 3 total. So the electronic geometry is trigonal, or sometimes called trigonal, planar. And then the molecular geometry, or what we also call the shape, is, so we need one that's a 3, 0. So 3, 0. So that is also called trigonal planar. And so if I were to redraw this with the shape, I would put the carbon here. I would probably like the oxygen on top, but you could put a hydrogen on top. And then it looks like one sticks out here and one sticks out here. Kind of like the inside of a Mercedes-Benz little circle thing. So it's divided in 3. So, and it's flat, it's planar. So if you look over here on the diagram, there's none of the little dashed lines because all of the bonds would be flat, like it will lay down flat. Now we have a lab where we'll make models, and so you'll be able to see when you get a trigonal planar one how it would lay down flat versus something that is tetrahedral, and then it has to stand up. Like it has atoms sticking in all directions, so it wouldn't be able to lay flat. I want to do one more, and yeah, so I was just trying to think. I was going to do HCN. I have one more after this that I want to do because I want to do another one with lone pairs on the middle. So HCN, and we came up with the Lewis structure in a previous video that looked like this. So again, we find our central atom, which is the carbon, the one in the middle, and we ask ourselves how many atoms are bonded to it. So there's 1, 2. Now notice I don't care that it's a triple bond. I am really just counting how many atoms are bonded to it because the triple bond all moves in the same direction. So double, triple, single, they don't change the shape. Okay, so how many atoms? 2 atoms, and then the carbon has 0 lone pairs. There's no dots on the carbon. Again, a lone pair would be like if there's dots on it, but there's not. All right, so this has a total of 2. And the 2 total is up here at linear. The triangle one here, this is the center one. So there's 1, 2. So the electronic geometry is linear. And if you look at linear, even though that's facing the wrong direction, 2, 0, if something's linear and only has 2 things around it, that's the only shape. Linear only has 1 shape. And that's linear. And so then if I were to draw this like a linear, it would look just like the Lewis structure I have because it's in a line. So it would look just like the Lewis structure. So let me do one more. I want to do another one that has lone pairs on the central atom. So I'm going to erase all these little marks that I wrote on this. And I'm just going to erase the top one. I can leave the bottom one there. And again, I'm erasing it now, but if you just rewind the video slightly, you can get it back, right? It doesn't erase it totally from the video. All right, so I was going to do NH3, which I think I also did on the Lewis structure, and it has 3 hydrogens around a nitrogen, and the nitrogen does have a lone pair. So if I were doing the shape, I would look at the center atom, and I count how many atoms are bonded to it. And so I go 1, 2, 3. And then you look at how many lone pairs. Okay, nitrogen does have 1 right there. That's when I say how many lone pairs on the central atom. That's what I'm talking about. So there's 1 lone pair. So this is an example of 4 total groups around the center atom, and 4 total groups always have an electronic geometry of tetrahedral. Now, tetrahedral can form different shapes depending on how many lone pairs there are. So this is a 3, 1, so that would be trigonal pyramidal for the shape. And trigonal pyramidal looks kind of like a pyramid. You have the nitrogen in the middle. It would have one hydrogen here, and then one hydrogen would be behind it, and one would be coming out. So it would be sitting up kind of like a pyramid. And then on this one down here, they draw a line for the lone pair. Usually I wouldn't draw the line. I would just draw the lone pair. I think they did it in the chart for emphasis, but it would have a lone pair on the top. And surprisingly, or maybe not surprisingly, lone pairs take up more space than bonded pairs. So they actually will push the bonds down a little bit more when there's lone pairs. So this would be how we would draw the VSEPR structure of that to show its shape. So that's the examples I'm going to give you. And hopefully you've either tried the lab or the lab has some more examples that you can practice, along with a computer simulator that you can put in the bonds, and it will look at the central atom and kind of give you another visualization of shape.